Well, thank you very much, Mel, for opportunity to speak here, and thank you everyone for coming. So I'm going to talk about some theory that is essentially in its very infancy. Like a couple of years ago, I'll be honest, I was blissfully unaware of Kirch topology at all. Some people here in the audience, I'm sure, knew about this. So anyway, let's start with that. So one way to define Kirch topology is by, like any topology, by the basis of open sets. So it's a topology in its original form on N, which for the purpose of this talk will start from 1. And for the basis of open sets, we take all square free D. And for each such D, we take some A, which is co-prime to D, and we look at all X that are congruent to A mod D. So that's kind of the basis of our topology. And it goes back to 1969 paper by A.M. Kirch in Monthly, very short paper. And without the square free condition, this is Golomb topology. That goes back a little bit further to 1953 to talk, and I think a little publication by Morton Brown, and then independently Solomon Golomb, 1959. And it seems like for most of the time since then, this was just kind of like a curiosity, a funny topological space. It's Hausdorff connected and locally connected. Kirch topology is locally connected. Golomb topology is Hausdorff connected, but not locally connected. Here's a good way to think of Kirch topology that kind of goes back to the talk of Mel. Same group, product Z over PZ for P prime, and N embeds there. And we can handle this group with a product topology where on each factor, we have some strange topology. It's almost discrete, but not quite. So all non-zero singletons are open, but 0 is dense. So the only open set that contains 0 is the whole Z over PZ.
That makes it what's called a generic point?
Exactly. So we basically take then the product topology, so all the cylindrical set, and restrict to N. Another way of saying this, we consider the weakest topology for this, all these maps are continuous. Let me make a little remark that Kirch topology is not metrizable. In fact, there cannot be a countable metric space that is connected. Because if you fix a point and consider distance to the point, that's automatically going to be a continuous map. And map to R with a countable image, there will be a real number, which is not an upper bound, but not in a image. And then if you take pre-image of all those at a distance less, so take all the points at a distance less than this R, it's an open set. All points at a distance greater than this R, that's another open set. And their disjoint union is your space. As a good reference for this, there is a paper by Clark, Lewis, Lockhart, and Pollock, 2019, on Golomb topologies that talks about this. And there have been other generalizations, but still, I think people have really not found any way to use such topologies. Even though it's been a while since they were first constructed. Let me explain some of these properties. The Hausdorff property is actually the simplest. It's immediate. So Hausdorff means given any two distinct points, you can separate them by open neighborhoods. So you just fix a prime that's greater than both A and B, and look at all elements that are congruent to A mod P, and all that are congruent to B mod P. And these are those basic Kirch open neighborhoods. They do not intersect. Local So local connectedness and global connectedness actually comes from this statement. Those basic open sets are themselves connected, and U sub 1 is the whole N, so that global connectedness, but the local connectedness is the most interesting part here. And before proving this, let's prove the following rather interesting lemma, just a characterization of the closure of those basic open sets. So let me remind you, U sub AD, D is square free, and then for every prime P dividing D, we have X congruent to A mod P. And for the closure, X is congruent to A or 0 mod P. That's how the closure is going to look like. For the proof, well, first of all, it's easy to see that this set that we want to show it's a closure, it is actually closed because the complement is open. The complement you can easily see as a finite union of some basic open sets. Now, why is every element in this? Like, what do we need to show? We need to show that you have any element, let's say n, so any natural number n, which is A or 0 modulo every prime dividing D, then every neighborhood of it will intersect with U sub AD. So take this n, take some neighborhood of it, a basic neighborhood, U sub n d prime. Now, here's the thing about intersecting two arithmetic progressions. Two arithmetic progressions, like A, D, and ND, they will intersect if and only if n minus A is the multiple of JCD of D and D prime. Or another way of saying it, if they don't intersect, there is a prime. Remember, D and D prime are square free. So there's a prime dividing both of them such that n and A are different modulo that prime. But if n is not A modulo P, by the definition, it's 0 modulo P. And if it is 0 modulo P, but P also divides D prime, that's not possible because of the Kirch condition that JCD of the number n and D prime in the open neighborhood is 1. I know it's not always a good idea to do proofs in talk, but I wanted to do this at least to give you an idea of the level of complexity of this proof, which is rather low. Any questions before I go on? Okay, so here I just reproduced the statement of the lemma and the theorem for your convenience. And now let me prove the theorem. Suppose our U sub AD is a disjoint union of two open sets. Take an element A sub 1 in the first one and A sub 2 in the second one, and the corresponding basic open sets. The inclusions, so we have this U sub A1 D1, which sits inside U sub AD. And if one arithmetic progression sits entirely inside the other, that means that the common difference of the bigger progression divides the common difference of the smaller progression. So D actually divides both D sub 1 and D sub 2. Now we can take some natural number n, which is A modulo P for all P dividing D. That's another way of saying it's in U sub AD. And it's congruent to 0 modulo all primes P that divide D sub 1 or D sub 2, but not D. By lemma, this n is in a closure of both of these basic neighborhoods, U sub A1 D1 and U sub A2 D2. But it's also in U sub AD, so it's in one of those U sub 1 or U sub 2. And if it's in U sub 1, and it's in a closure of U sub A sub 2 D sub 2, so U sub 1 will intersect non-trivially with that closure, and that's a contradiction to U sub 1 and U sub 2 being disjoint. And same for the other choice, clearly it's symmetrical. So again, the proof is nice, not at all hard. All right, let me talk about the other side of the story, which for me actually came first. And then I realized that this very much goes nicely with Kirch topology. So I thought about this local integer polynomial functions first. It's just kind of trying to make sense of some of the results of my former PhD student. In his thesis, he worked on polynomial iterations, and I realized, well, everything applies to functions that are not necessarily polynomial, but what I call local integer polynomial. So here's the definition. Suppose X is a subset of Z. Usually it's going to be infinite subset. By lib of X, we denote the ring of all energy valued functions on X, such that if you restrict them to any finite subset of X, it can be given by a polynomial with integer coefficient. Clearly, it's a ring and it contains just integer polynomials, but it's actually much bigger. Immediate question is, I say it can be given by a polynomial with integer coefficients. Equivalently, actually, we can just say that an interpolation polynomial is in Z of X. It's not hard at all to show that if some polynomial with integer coefficients gives you the values at a finite set S, then the interpolation polynomial also must have integer coefficients. Here's the example of what kind of condition on integer valued function this Leibniz imposes. The set S, well, if it's a singleton, this is automatic because we require the functions to take integer values to begin with. If it's a two-element subset, the condition is very classical, that difference of inputs divides the difference of outputs. And for larger S, we have somewhat more complicated conditions. This is what's going on for infinite X. Well, Z is inside Z of X will be inside lib of Z, which inside lib of X. And the first two rings are countable. The other two rings have cardinality continuum. The last inclusion is by restriction. If you have function which is lib on Z, it will be lib on any finite subset of Z.
Any finite subsets of X.
And one can show that this is, in fact, an embedding, that this restriction is injected, which we'll see in a moment. Now, why is there cardinality continuum? This is why. The X is infinite, so it's countable. Suppose we have a bijection from N to X. Then for any sequence of integers starting with A sub 0, A sub 0, A sub 1, and so on, we can construct this infinite sum. A sub 0 plus A sub 1 times X minus the first element, plus S A sub 2 times X minus the first, X minus the second, plus and so on. The sum will pretty much diverge for any real number, except it will converge for all elements of X, because for each element of X, from some point on, we just get all zeros. And for the same reason, for any finite subset of X, it will be given by a polynomial in Z of X. Moreover, one can see that, in fact, there is a one-to-one correspondence between lib functions on X and these sequences of integers. In other words, given a lip function on X, we can just one by one find the a sub 0, a sub 1, and so on. For example, a sub 0 is the value at the first point, at sigma of 1. And so on, and they will have to be in Z. So there is a bijection. The bijection depends on how you count elements in X. And these coefficients, they behave nicely with respect to addition, but terribly with respect to the product. We will call these expressions product sums. Here's an example that's most kind of appropriate for us. If X is an arithmetic progression, like a basic Kirch open set, it's natural to count like A plus D, A plus 2D, and so on. And then this product sum becomes what you see here. And we want to think of these product sums as like power series, especially for such X. And we kind of have the right to do this because if we define a version of discrete derivative, which if we are an entire n is just f of x plus 1 minus f of x, but if we are on an arithmetic progression with a difference d, we can say it's f of x plus d minus f of x over d, which will still be in z of x if f is in z of x. And in fact, so this will be from lip to lip.
This is very close to standard material on interpolation theory, Newton series. You're just, at this point, it's just a minor difference accounting for the fact that we need integer coefficient polynomials and not integer valued.
Precisely. It's very much related, yes. And so what I basically, with respect to this kind of discrete derivative, when the derivative of the product of k factors is k times the derivative of the product of k minus 1 factors, just like for the usual parts. All right, let me talk a bit about algebraic properties of lip of x for infinite x. I actually talked about the subject first at the seminar in May 2024. I don't know how many people in the audience were there then, and I doubt even those who were remember much, so let me briefly talk about this. First of all, if we have a lip function on some infinite x, which is 0 on an infinite subset of f of x, then it's just 0 on the entire x. And the proof is immediate. Just the difference of inputs divides the difference of outputs. So let's take one of the inputs to be our a and the other to be x, such that f of x is 0. And we'll get that a minus x divides f of a. And this happens for infinitely many x, so f of a has to be 0. This is the reason why the restrictions are injected. And there are two other simple facts that are done in the same spirit, based on this. On one, that lip of x is a domain, and the units are just -1 and 1. In fact, these
what do you mean that it's a domain?
No zero divisors.
No, yeah, okay.
Yeah. And right, the word domain has many meanings.
And the multiplication that you're thinking of is point-wise, it's value-wise.
As functions, yes. It's a subset of the ring of integer valued function, which is, of course, very much not. So, in fact, for these four things, we just need the Lipness property for two-element subsets. The next two, we do need the full strength of Lipness. If you have an element in z of x which is irreducible, so prime or a polynomial with content 1, then it remains irreducible in lip of x. And z of x is algebraically closed in lip of x. Here's something that I did not know when I talked about this first. time here, lib of x is not Noetherian for any infinite x. And this comes from the following observation. You see, all elements of lib of x are infinite sums, but some of them are actually infinite products. You can do a similar construction as infinite sum with infinite products, each product being 1 plus, and then product of, or some constant times product of x minus x sub I for ever increasing subset of x sub I. And once you have those infinite products, just chipping away the first term, the first two terms, and so on, you can get a strictly increasing sequence of principal ideals. So, not Noetherian. I actually know very little about the ideals of this string. It could be quite rich, but where I'm going to go is kind of a rather different direction. Local lib function. So you see, being lib, even though there is a word local in a name, is a global condition. And when we have a topology, it's natural to localize it. Now, Kirch topology seems exceptionally well suited, not least because when you look at those product sums and you see where they converge periodically, you realize immediately that it will converge periodically at any point in integer periodic point that has infinitely many elements in X equal to it mod P. So mod P square, mod P cube doesn't come into play at all. It's mod P that's essential. And which is why kind of Kirch topology and non-Golomb topology is, to me, most suitable. There are other reasons as well. So essentially, in other terminologies of algebraic geometry, lib functions on Kirch open sets form a pre-sheaf. And what we're looking for is a sheafification of that pre-sheaf. So here's the definition. Function, so suppose U is a Kirch open subset of N, and then f from U to Z is called locally lib. If for any element in U there is an open neighborhood of it, such that the restriction of f to that open neighborhood is lib. And we denote this sheaf by math-cal lib. This is a sheaf of locally lib functions. I want to emphasize the analogy with one of the possible definitions of complex analytic functions. A complex analytic function on U is such function on U that at the neighborhood of every point, it can be given by a convergent power series. And we have a very similar situation. At the neighborhood of every point, Kirch neighborhood, which is arithmetic progression, it is given by that product sum, which is very much an analog of a power series. Well, natural question, is every locally lib function on a Kirch open set lib? Well, the answer is immediate no. For example, consider Kirch open set, which is all numbers that are not 0 mod 3, which is the union of two non-intersecting Kirch open sets, those that are 1 mod 3 and 2 mod 3. And we take any lib function on one of them, for example, constant function 1, and any function on the other, for example, constant function 0. And it's locally lib, but not lib. In general, whenever you have a sheaf and you have two non-intersecting open sets, you can take anything on one and anything else on the other, and there doesn't have to be any interplay. So the answer is no, but there's a better question. Is every locally lib function on a connected open set lib? That's a much better question. And you have a partial answer. So in general, probably not. Although technical, I don't have a counterexample. I just have an example for which I cannot prove that the answer is yes, and I suspect strongly that the answer is no. But we do have the following theorem. So every locally lib function on a basic Kirch open set is lib. The proof is completely elementary, but not completely obvious, and I will explain in the rest of the talk. Most of the rest of the talk is to explain what goes into that proof. This theorem can also be generalized not to one such open set, but to an arbitrary union of this basic open neighborhood of the same point A. And as a result, given Kirch open set and A in there, we can just look at all the Kirch basic open sets, so those U sub AD that are contained in U, and every locally lib function on U will have to be lib on the union of these sets. And we can go even one step further and replace in both of these results basic sets with almost basic, which is when you have the arithmetic progression, which is Kirch basic open set, and you remove any finite collection of elements. Remember, Kirch topology is Hausdorff, so singletons are closed. And so when you remove finitely many singletons, it's still an open set. So to prove something like this, we need some terminology. And the very first terminology I want to describe is circuits. Here is the definition. Suppose the function f is not lib. What that means is that there is some finite subset on which the interpolation polynomial is not in Z of x. So it's natural to consider minimal such subsets. And that's exactly what we're going to call a circuit. A finite set x, so here x is a finite subset of U, is a circuit for f if the interpolation polynomial for f on x is not in Z of x, but if you remove any element from x, it becomes in Z of x. The terminology is borrowed from the theory of matroids, and they in turn borrowed it from graph theory.
But you don't actually have a matroid here, do you?
I don't think I have a matroid. It's not a matroid, no. Here are some examples of circuits. So circuits of size 1 do not exist because we require functions to be Z. That's really the reason. If we only looked at functions to Q, then yeah, we would have circuits of size 1. Size 2, two elements A and B, where A minus B does not divide f of A minus f of B. But there are circuits of higher sizes. For example, 135 for a function which is 1/2 x minus 3 squared, which is a totally fine integer valued functions on a Kirch open set of odd integers. By the way, that Kirch open set of odd integers is dense in N in Kirch topology. The restrictions to 1, 3, 1, 5, and 3, 5 respectively are 3 minus x, 2, and x minus 3. So I don't have a full classification of what circuits are, but I do have some decent understanding of them. And in particular, I have this lemma. So suppose X is a circuit for F. So by definition, that means that the interpolation polynomial has some non-integer coefficients, but actually more is true. Its coefficient for the highest power, and that highest power is x to the size of x minus 1, is already not in Z. And if D is denominator in simplest terms, then all elements in X are in fact congruent modulo D. So the minimal arithmetic progression that contains all of those elements of the circuit, which I view as kind of a convex hull, I call it arithmetic closure of this. I mean, I don't know if I'll ever put it in anything published, but that's how I think about it, is not the whole n. Here is the proof. It's rather simple, so let me, and it's important, so let me explain. We just, for every element x sub I in X, so let's say X is from X sub 1 to X sub n, we compare the interpolation polynomial for F and a whole set X and an X without that element. Sure enough, the difference is 0 on all other elements, and from the degree, we get that the interpolation on a whole X is the interpolation polynomial on X without X sub I plus some constant C times the product of X minus X sub K for all K that are not I. And in fact, that constant C is the same for all I. It is precisely the coefficient for X to the n minus 1 in the interpolation polynomial for F on X. And because the interpolation polynomial for X without X sub I is in Z of X, and for whole X is not in Z of X, the C should be not in Z, which is exactly first statement of what we wanted to show. For the second statement, we replace I by J in the above formula and subtract. And so on the left, we just get 0. On the right, we have the difference of two polynomials in Z of X plus C times the difference of products that have a lot in common. They have in common the product of all the X minus X sub K for all K that are not I nor J. And we also have X minus X sub J minus X minus X sub I. Simplifying that last parenthesis to just X sub I minus X sub J, we get that C times X sub I minus X sub J times this monic polynomial with integer coefficients is in Z of X. So C times X sub I minus X sub J is in Z, which precisely means that the denominator of C divides X sub I minus X sub J. And that is what we wanted to show for part 2. So nothing harder. Here is another lemma about circuits, which is somewhat more complicated. I call it circuit improvement lemma. Suppose X sub 1 and so on, X sub n is a circuit, and M is any number from 2 to n. Suppose E belongs to the smallest full arithmetic progression that contains X sub 1 and so on X sub m. I will denote this now and later in the talk with these less than greater than brackets. Then what I say is that essentially that I can replace one of the X sub i's from this X sub 1 and so on X sub m by E and still have a circuit. That's not quite correct. I might not get a circuit, but I get something where F, interpolation polynomial for F is not in Z of X. So in particular, if I consider the circuit an original circuit of the smallest size for F, then that new thing will also be a circuit. I'm not going to give you a complete proof. Let me just say that it's kind of similar in spirit. It just worked with the interpolation polynomials to the previous proof. But I'll explain why this is even feasible in the simplest case where n and m are 2. So our circuit now is X sub 1, X sub 2. And E is in the arithmetic progression generated by X sub 1 and X sub 2. Because X sub 1 and X sub 2 is a circuit for F, the difference of inputs does not divide the difference of outputs. So F of X sub 1 minus F of X sub 2, or F sub 1 minus X sub 2. By the way, this thing is called divided difference. In fact, for any n inputs, the highest degree coefficient for the interpolation polynomial is known as divided difference. Apparently comes a lot in numerical analysis, but it's a digression. If we, in this fraction, just subtract and add in the numerator f of e, or rather break this into the difference of fractions, we get this first equality. And then to get from the first, the second equality is by multiplying, say, in the first fraction and dividing by x sub 1 minus e, and same for the second one with x sub 2 minus e. And then this ratio, x sub 1 minus e over x sub 1 minus x sub 2, is integer because e is in the progression generated by x sub 1 and x sub 2. And same for the other little fraction. So if the other two fractions are all integers, then the original fraction has to be an integer, and it's not. So one of those two other fractions are not integer, and that exactly means that one of those circuits obtained by replacing x sub 2 by e or x sub 1 by e is a circuit. All right. This is a curious fact that plays quite a bit of a role in this theory. Given any finite collection of arithmetic progressions, if they intersect pairwise, then they intersect altogether. Another way of saying it, if you have a finite collection of concurrences, if there is no common solution, it's because for two congruences, there's no common solution. It really follows from Cheney's remainder theorem. Checking intersection you can do for individual prime, and for individual prime power. For individual prime power, if two things intersect, one is contained in the other. That's one way of thinking about it. So suppose we have u sub 1 and u sub n, these intersecting or pairwise intersecting arithmetic progressions, and f is the function in their union. Then if we slip on each of them, it's slip on the whole union. I'll give you the proof for n equals 2. For general n, it's not that much different. So suppose f is not lip on a union. Consider a circuit of the smallest size for f with the smallest number of elements not in the intersection. So it must contain, if it's a circuit, it must contain some x sub 1 in u sub 1, which is not in u sub 2. It cannot be all inside u sub 2. And it cannot be all inside u sub 1 either, because the function is lip on that. So there is x sub 1 in u sub 1 that's not in u sub 2, and x sub 2 in u sub 2 not in u sub 1. Consider the arithmetic progression generated by x sub 1 and x sub 2. By the curious fact, it intersects the intersection of u sub 1 and u sub 2. So by the circuit improvement lemma, we can, and once it intersects infinitely many places. So by the circuit improvement lemma, we can replace x sub 1 or x sub 2 by some e in the intersection, resulting in fewer elements. We have another circuit with fewer elements outside of the intersection. And so that's a contradiction, and so that's the proof in this particular case. Any questions? All right, now let me continue to explain how kind of the main theorem, which is if f is lip, it is locally lip on u sub ad, then it is in fact lip on u sub ad. Where u sub ad, that's the Kirch basic open set. Well, natural numbers that are congruent to A mod D. I'm not going to give you a complete proof, but of course, but just an outline and the main ideas. Suppose F is not lib. Consider a circuit of the smallest size. And because our F is locally lib, each of those x sub i's in the circuit comes with a neighborhood u sub x sub I d sub I on which F is lib. If all of these neighborhoods, equivalently any two of them from that curious fact, intersect, then F is going to be lib on their union from the previous theorem, which is a contradiction, because if we slip on their union, it cannot have a circuit X. One way this could happen this could happen if JCD of D sub I and D sub J, which are the differences of those neighborhoods of X sub i's, X sub I and X sub J, is 1 for all I not equal to J. And we're in a Kirch topology, so we have a way to ensure this. If X sub I is divisible by all prime that divide D sub J, which really means divisible by D sub J, then D sub I cannot have any of these primes. And so JCD will be 1. Because remember, in Kirch topology, U sub X sub I, D sub I, JCD of X sub I and D sub I is 1. And so such circuits are not possible. What if we have an arbitrary circuit? And we're going to improve our arbitrary circuit to the circuit which we know is impossible. We do that using the circuit improvement lemma, which we first apply to the entire circuit to replace one of the what we will consider old elements by a new element. And then we have n-1 elements remaining, so we will apply circuit improvement lemma for m being n-1 to that subset of old elements, and again replace one by the new one. In other words, we never re-replace. We just replace the old by the new. The last step in the procedure, we only have two elements left, and we replace one of them by something in the arithmetic progression that they generate. So we will left with just one old element and n-1 new elements. And here's the idea of the proof that every time we do this, we just make sure that our new element is divisible by any primes we could possibly make it divisible by that could possibly ever matter. Specifically, what primes could matter? These are the primes that divide the difference between any elements of your set, of your circuit at this point, and also divide any of the D sub i's for the neighborhood. Can we always make our new element divisible by that? Not quite. But we cannot make it divisible essentially in one situation, where all the old vertices are the same modulo some prime p, and that same is not zero. Okay, so in this case, we have no choice. We cannot do anything. Our new element would also be the same modulo that prime p. But in all other cases, we can make it divisible by p. And so that's what we do. And at the end, almost magically, we will get a circuit where any two neighborhoods intersect. I'm not going to go into the detail. I don't think it's reasonable to try to understand that live in a talk, but the proof is not hard. And that is now essentially the complete proof, modulo all the preliminary results. So what does this theorem really imply? If you have a local elliptic function and you have a cover of your U by basic open sets, then we know that a local elliptic function is just lib on those sets. And so every local ellipse function given, so if we fix any cover, we can say every local ellipse function just comes from a collection of lip functions on each U that match at the intersection. In the terminology of the sheaf theory, this means that the space of global sections of lip on U or U with coefficients lip, which is really, this is the set of all those local ellipse functions on U, can be calculated from any open cover by the basic open sets from just the lip pre-sheaf by what's known as a check cohomology construction. So what is check cohomology construction? Very general kind of way to talk about cohomology of sheaves. If you have U an open cover of U, you can construct out of it some complex of, well, abelian groups in the following way. You have just a direct product of functions on individual U sub i's. Direct product of function of pairwise intersection, direct product of a triple intersection, and so on. And you have the maps going that's given by restriction and alternating sum. And in particular, and then you just do cohomology of that complex. And in particular, H0 that you get from this construction from the particular cover is precisely what I described. Now, in general, like finer covers could give you different cohomology. And on the other hand, if your open sets are what's known acyclic, they kind of don't have cohomology of their own, contractible or affine in algebraic geometry setting or coherent sheaves, check cohomology for any affine covering will calculate the correct cohomology. So there are two things here. The check cohomology in general is injective limit of these guys for finer coverings, but also there's, I mean, usually when we have like sheaves, and we can talk about category of coherent sheaves, and usually there are enough injective there, so you can talk about higher direct functors to the functor of global sections and have those kind of cohomology. And in many situations, like coherent sheaves on coherent sheaves on schemes, those would coincide. Well, and so the natural question to ask for H0, this is true, is it true for chi cohomology? In other words, are these open basic Kirch open sets actually acyclic? And I suspect yes. Moreover, I suspect that the answer is yes, even for these kind of star-like sets, which are unions of various Kirch basic neighborhoods of a given point. I don't have a proof, but I do have this little lemma. Like if this were not true, I would not have suspected what I just said. So suppose U sub 1 and U sub 2 are two basic open sets, open neighborhoods of the same point A. Then every lip function on their intersection can be written as a difference of restrictions of lip functions on U sub 1 and U sub 2. So it's not completely obvious. And here's the idea of the proof. Essentially, our products and a product sum form kind of a basis, not really, but kind of a basis. And what we can show that if we have any two products, one product for U sub 1 and another product for U sub 2, then we can find a product in the intersection that belongs to the ideal that these two guys generate. Now, it might not be the product of x minus the intersection, points in the intersection of these guys. You may have to throw in more elements, but you can always do. And because of that, if you have any function which is lib on the intersection, you can just write, well, before that, like you can find these triples that exhaust simultaneously u sub 1, u sub 2, and the intersection. And then you find for every function lib on the intersection, you can write it as the sum with polynomial coefficients of products from those collections. Each of those products can be rewritten again with polynomial coefficients as the difference of some product of x minus x sub I for x sub I and u sub 1, and the other for x sub I and u sub 2. And this way we can write our lib function on the intersection as a difference of two product sums with polynomial coefficients. Now, our original product sums by definition had just integer coefficients, and that gave us uniqueness for those integer coefficients. But instead of integer coefficients, we have integer polynomials, we would still get a lib function. It's just those integer polynomials are no longer unique. And so this is how this proof goes. And I think I can generalize it quite a bit, but I mean, there are many things here that I do not fully understand. And so let me talk about some future goals. The very first one is to understand the cohomology of the subject that I just constructed. Like whether it can be calculated from just these basic open covers and check cohomology construction. And what are they? For example, if we consider, and this is a Kirch open set of all natural numbers that are not divisible by 6. It's a union of 3 basic Kirch open sets. 1 mod 3, 2 mod 3 that do not intersect each other, and an odd numbers that intersect both of them. Then I don't know, although I do suspect that local lib function on this is not always lib on the whole thing. But kind of only because there could be powers of 2 in the denominator. And I also suspect that H1 of this is non-trivial. But I have no idea, for example, cohomological dimension of N. There's so many questions I just don't even have enough intuition to answer at this point. Explore possible generalizations. Well, first of all, whenever there's a sheaf of rings, there are coherent sheaves of modules over that sheaf of rings. Besides integer valued functions, we can make functions that are valued at other nice rings. Well, you can localize Z, but also you can consider some algebraic numbers, cyclotomic integers in particular would be quite nice. You can generalize the space from N to, I mean, similar things for some algebraic number fields. By the way, instead of N, we can consider non-zero Z, like Z without 0. I'm not sure how much the theory would change. I mean, the Kirch topology has been considered for that as well, and most of the things will go right away. I mean, everything will, technically, the things I said will all be true. Now, I am not a big fan of defining new objects for the sake of studying these new objects. Like, I do not do category theory. And to me, every new theory has to give back to the old. And this is the very first test that I'm trying to see if I can reprove or at least reinterpret quadratic reciprocity law. I don't think it's unreasonable. I have in mind some particular sets, Kirch open sets, say for different primes P and Q, on which somewhere in cohomology may sit some non-trivial elements, I would say in the first cohomology, but I don't have a proof, otherwise I would have presented. But this is certainly something very much on my radar, trying to understand it. And finally, one more goal, find a good name for this theory. I don't have one. And arithmetic topology is already taken by a very nice theory, of which I heard actually back in the 90s, although when I was in grad school, although I thought that this was more than just a collection of wild observations, I don't think it was, and definitely now it's much more developed. The main premise of this theory, according to the author of this book, Masanori Morishita, is that Gauss, when he was young, did two things: quadratic reciprocity law and Lincoln number of knots. And it's unclear if he realized that they're very much related to each other, but they are. So the premise here is that in étale cohomology, Z is up to 2 torsion, has cohomological dimension 3. So it's like three-dimensional manifold, and primes are like knots, and square-free integers are like links. And to understand that, basically what's going on, there is some analogy, very serious analogy between some invariance of knots and links and things that come up, invariance of Galois group of extensions unramified outside of one or finite collection of primes. So it's a very high-tech theory. What I'm doing is very much low-tech, so I cannot get on a bandwagon of this theory. So I need a name. And with that, thank you very much for attention.
Thank you.
Thank you. And thank you, Mel.
Are there any questions for Alexander, and who just gave us a lecture on Borisov theory?
No.
Surely an unfair question at this point, but do you have anything new that you'd want to prove, or
Anything, sorry?
anything new that you want to prove?
Well, obviously, I would think that there should be applications beyond just reproving, but I mean, I need to start small. I have to at least understand quadratic reciprocity. But maybe if I can understand, like ideally, what I would like to have some non-trivial cohomology group in which you can see quadratic reciprocity as just one little piece of it. But I mean, this is just a dream at this point. I have no idea.
Other questions for Alexander? If not, thank you again.
Thank you, and thank you, Mel.
Yeah. So Alexander, can you just close your slides?
Yeah.
Excellent. Good. We're back in business. See, next week, Bruce Resnick, I believe, is on deck. And then we have a somewhat extended Thanksgiving break, and we're back in December after that.
Mel, can I ask Alexander the last question?
Of course.
Sure.
Alexander, about your similarity between the knots and primes. You have said the knots like a prime. What about the equivalence between the knots? Can you give a flavor? How deep is this similarity?
I don't know.
It is only the first glance or something much deeper?
My understanding is that this is something much deeper. But I really I mean, it's one of my goals is to read that book on knots and primes, but I haven't gone far at all. I do know that it goes beyond the classical theory. So classical theory is a small part of this.
Okay.
So, yeah, I cannot really talk about that other theory at all.
Your statement is very, very promisable about the similarity. It can be catched something because there are a lot of the unsolvable here and there, and this is why.
I mean, it's like you said, this theory with the algebraic topology. I mean, some pretty big people kind of were responsible for creating this. I mean, going back supposedly to Gauss, but for example, Barry Mazur and Yuri Manning were at the beginning of that as well. So, but I have some idea of that theory, but very weak.
Okay.
I mean, the book, though, I mean, is really looks really well written. This Masanori Marishita book.
Okay. Thank you. Even this idea, similarities, a Miraggio is also very nice. I mean, the Fata Morgana, yeah. Good. Thank you very much. It was very interesting.
Alexander, I'd like to ask you, what is your intuition concerning the quadratic reciprocity law and its relation to this topology?
So there are two things that I'm thinking about. Given two odd primes, if you look at
Leonid, could you mute?
All numbers that are not zero mod p times q, then you can say that it's the union of those that are not zero mod p and not zero mod p. Not zero mod p, though, is like a disconnected set. And the other is also disconnected set, kind of intersection like this. I do not know if H1 there is zero or not, may or may not be. But there's also another thing which you can do. Those numbers that are not zero modulo, numbers that are not divisible by QPQ. And then if you look at odd numbers that are not zero mod P, that is a connected Kirch open set. Like you have odd besides zero, because besides those numbers that are not zero mod P, there's also kind of odd numbers cutting across. And that intersection of two such guys, that's, I think, more promising, where like this is more promising to look at these. But I'm not there yet. But I kind of think about this way: the Legendre symbol is locally elliptic function if you exclude those that are divisible by p, which is trivial, but that's a start. And you know, with Euler's identity, it's congruent to actual polynomials. So it's not that far from what we're doing. And of course, there are hundreds of proofs of quadratic reciprocity. So
Carlos, you're muted.
Okay. Yeah, I just feel that the squares inside the integers contain a great deal of information that is not quite obvious, and reciprocity, quadratic reciprocity, captures a little bit of that information. So I just feel that somehow in this topology, the set of squares, of subsets containing the squares, probably have some relevance to this question of
that could be true too. The set of the squares actually is closed, I believe. like if something is not a square, you can come up with a Kirch neighborhood is also not a square.
Right, right.
And so so it's another thing that it's on my radar for the quadratic reciprocity.
Oh, okay. All right.
Yeah, that could be too. Yeah.
Yeah. All right. Okay. Thanks. I mean, it's very, very interesting. Yeah.
And I got it very. I mean, I've been looking for like this, and I've been working around this connection between like this analogy in algebraic geometry and number theory. I mean, because I'm both algebraic geometer and a number theorist. My whole career, so to speak, I was looking for things like that, and I was completely unaware of Kirch's Kirch topology.
Now, at the beginning of your talk, I was trying, but didn't try hard enough to essentially view the definition of the topology in terms of picking up certain points on the unit circle that would be roots of unity, and that would correspond to arithmetic progressions. But it probably needs, one has to look at it more carefully. I mean, selection of subsets of points on the unit circle corresponding to roots of unity in a very particular way that encodes the moduli. So I just feel there somehow one is given a new topology to the points on to the basically torsion points on the unit circle, but I cannot wrap around my my head and you know this that would be a way to connect it to some reciprocity law, but
like the nicest proof of quadratic reciprocity that I know, I think due to master, is you have this like for P and Q you consider x to the P minus 1 over x minus 1, and well you divide by x to the P minus 1 over 2, so you get polynomial in x plus 1 over x. Right. Essentially scale Chebyshev polynomials, and then quadratic reciprocity becomes essentially just a statement about resultants. That resultants
right.
Right.
Yeah.
Resultant is plus or minus, and it's plus or minus 1 and switches.
Yeah, so it's really interesting. Yeah. Okay. All right. Thanks.
Other questions or comments or remarks on the state of the universe?
If you're doing the latter, you might want to turn off the recording.
Oh, thank you. Yes.